All right, guys, welcome to the lab. This is Lab 7 where we're discussing MTF. I'm Evan, this is Caleb, and that's Logan.
So in this lab, we're going to be measuring the MTF of a diffraction-limited system. First, we're going to walk you through some of the theory and the concepts, such as MTF, PSF, and LSF. And then we're going to take you through our experimental setup and our design that allowed us to find the cutoff frequency of our lens and actually measure the MTF. So let's get into some theory. So the modulation transfer function, or what we call the MTF, is a ratio of modulation in the image to the modulation in the object as a function of the frequency of a sine wave pattern. This is a universally applicable measure of the performance of an imaging system. So for a diffraction limited system, the MTF is related to the size of the diffraction pattern by this formula right here. The limiting resolution of a diffraction limited system is known as the cutoff frequency, nu naught, which is shown here. The diffraction pattern resulting from a circular aperture has a bright central region known as the Airy disk, and this is called, the Airy pattern, but mathematically it's represented by the bezel function. Huygens principle tells us that the wavefront that propagates through this aperture is a combination of spherical waves from the first wavefront. So when we talk about a collimated beam versus a focused beam going through a circular aperture, the pattern that we're going to see in our viewing screen is going to look the same between the two because we're passing through the circular aperture, and that's what really determines what our diffraction pattern looks like, which in this case is the Airy pattern. However, collimated beam and a focusing beam do differ in the fact that a collimated beam will have a different K vector. It will have a single K vector going through than the focusing beam, which is at a different angle. And this will affect the diffraction pattern we see on the screen in terms of its intensity and position. But the biggest difference is that focusing beam will have diffraction patterns at the focus position, as well as our other Airy functions at the NF, or the Fresnel number, plus or minus 1. The collimated beam, there's only one K vector, so we just have the Airy function at one position.
So based on this equation that we see here, we know that OPD and Fresnel number will increase with decreasing L. We also know that aperture size is a quadratic relationship with Fresnel number. So one of the most important things that we need to consider as optical engineers is aberrations. And there is something called a diffraction limited system, which means that our aberrations are not dominating. Instead, the limits of diffraction itself are.
So you can see at this point we have three half waves of defocus. You can see this by the black ring and the red in the middle. Next, if we move it to the left, you'll see that we have plus one wave of defocus with a black dot in the middle. Then if we move to the left of that, we'll have best focus, where you can see it's a full red uniform beam with an NF equal to 0, and that's best focus. All right, so we're going to try and make a diffraction limited system. To do this, we need to adjust the iris, or the aperture of the system, to where we're going to get an Airy disk of diameter 200 microns. And when we did the calculations, we got the aperture size to be 7.7 millimeters. So we used a microscope to measure the distance, or the diameter of the iris, to make sure it's 7.7 millimeters. Next, we had to measure the slit right here. We want this to be 1 over our cutoff frequency. And our cutoff frequency was about 12,000 hertz. And we want the diameter, or the width of the slit, to be 1 over that. And we got about 0.08 millimeters.
That's right. Everything that was just said was absolutely correct.
Okay, so looking at the setup, we have our laser going into our Keplerian beam expander, just like previous labs. To our mirror, this is our test lens here. It is a 1,000 millimeter test lens. This is our aperture, our iris, where the diameter is 7.7 millimeters, down to our slit and our power meter. All right, so using the slit that we described earlier, we're going to measure the LSF of our diffraction limited system. So at this position here, we have the minus one waves of defocus. Then we use the microscope to move it to the best focus position. Then we use the microscope again to move it to the plus one waves of defocus position. And at each position, we scanned our slit across and then measured the power on this power meter here. And then we got some beautiful plots that you guys will see soon.
So the first plot I want to show you guys is aperture size versus D, which is the difference between Z1 and Z2. And here you can see that that quadratic relationship that we described in the theory section is proven correct. Next, we can see these line spread functions at different focus positions. Here we see best focus, here we see plus one waves of defocus, and here we see minus one waves of defocus. We were then given MATLAB code that allowed us to transform this LSF function to an MTF function, and you can see these on the left of our graphs. On the right, we compare our experimental LSF to our theoretical LSF. In all cases, our experimental is pretty close to our theoretical values. Behind the scenes, we are actually taking the Fourier transformation of the LSF function and then normalizing that Fourier transformation of the LSF with the Fourier transformation of the LSF at the 0 frequency. We then modeled our system in Zmax, and you can see that we were able to create the same graphs that we created using the MATLAB code and measured experimentally. One thing that is important to note is that in Zmax, we had to specify +1 and -1 waves of defocus, and we were able to calculate these distances based on this formula as you see here. The result is that we needed to add in plus or minus 0.25 meters of defocus.